Hello everyone and welcome to the channel. In today's video, we'll be looking at questions in exercise 6, which covers all the translation step questions for chapter 5 and 6. So you guys know that whenever you're talking about selecting a material for a particular design, there are steps that you have to follow, which is first, before you start your selection, you have all the materials available for you. You have all the materials before you do any other thing. You have all materials available for you. Then first, what you have to do, the first step in selecting a material of your choice is to do what? Go through the translation step. This involves defining the function of the material, all the constraints that are in the material, the objective the material has to accomplish, and free variables. So after the translation step, now you can now go to screening. So with whatever you've done on the translation steps, with whatever you have on the translation step, this is what you use to go to the screening and screen out different material that doesn't meet your translation. So then after screening, you have like 4 or 5 different materials that passed all the screening. So there you now go towards ranking this material. When you have 5 or 4 different materials that have passed your screening, what you now have to do is to now use like a parameter or a property, like let me say the material index, or one of the property like yield strength or tensile strength, to rank these materials. Then at the end of the day, you now have to seek documentation. You have to read about all the materials that you've selected and see what they have been used for in the past, and know if the material is suitable for whatever you want to do with it. So in this chapter, we'll be going over all the questions related to translation, where we are trying to decide what is the function of the material, which is what does the component do. Then next, we'll now decide the constraints of the material, what are the essential conditions that must be met before you select that material. Like when you say it must have a yield strength above maybe say 20 gigapascal, something like that. It must have a tensile strength above 10 MPa, something related to that. So you have to make sure that it must be met. The constraint must be met. Then objective, there is no an actual value for objective. It can be high or low depending on what the objective is. If the objective is maximize, you want to make it as high as possible. You understand? If you want to make it if it's minimized, you're trying to reduce it as low as possible. Like in terms of cost, you're trying to make it less costly. So the lower the cost, the better. So after your objective, then you can now go to free variable. Then in the free variable is what you have the ability to change. It doesn't matter what it is. It can be choice of material. If you have like 2 or 3 materials that have passed the selection, it can be choice of material, or it can be the thickness of the material. So this is like a free variable, something that you can play with, something that you can change. It doesn't matter. So now you've understood this, let us now go into question 6.1. So for question 6.1, you can pause the video, take a second to look at the question. So this question, they are telling us to define the translation step, the function, constraint, and objective for this particular design. So I'm just going to write whatever we need. We need what? We need function. We need the function. We need constraints. We need objectives. And we need what? Free variables, right? Variables. So for the function, what I want you to know is that the function is always in the first line of this particular every question. In the first line of every question, that's where you see the function. So it says a material is required for windings. So you want to use the material to make windings for an electric arc furnace capable of withstanding high temperatures up to 1000 degrees C. So the name of this particular material is, what will I say, a high temperature electric arc furnace windings, or windings. Yeah, so you have function as what? High temperature electric air furnace windings. And also, you know that a winding, you guys have seen a transformer before, and you know that a winding is something like this. It's a wire that is drawn into coils like this. That's how a winding is. So let's go over to the constraint. So if you look at the question, the first constraint is something that must be met. So it has to be met before you select the material. So if you look at the first constraint that we meet in the question, it says it is capable of temperatures up to 1000 degrees C. So the temperature of the material, so this is function. So the constraint 1, the temperature of the material, the melting temperature Tm, must be greater than 1000 degrees C. That's the first constraint. The second constraint here, if you look at that, think about what attributes of the material must have if you want to make a material into windings and function properly in an electric arc furnace. So if you're looking at this winding that I've drawn over here, you can see in order to draw this material into wires, you have to use a process called wire drawing. So it must be ductile enough to be drawn into wires. So number 2, ductility, ductile enough for wire drawing. So now you've made the material. There is another function, another constraint that is related to this material. There is another constraint that is related to this material. Think about it. If the material is used in a furnace, in an electric furnace, that means it has to be conductive. So 3, it has to be conductive. Then the last one, if you're using this at very high temperatures, so with time, every material tends to, or every metal that is conductive tends to corrode. So you have to be corrosion resistant at elevated temperature. So corrosion resistance. So those are our function and constraint. Then objective is something that you can be as high as possible or as low as possible. That's the objective. So if you look at here, the objective is here. Objective is to minimize cost. So minimize cost. Minimize, and just go back. So objective is minimize cost. And the free variable is the choice of material. So let's go over to question 6.2. For question 6.2, take a second, pause the video and read the question. So in this particular question, we are trying to determine the function, constraints, objectives, and free variable of this particular design. So first, let's go with function. So for the function is always most times in the first line. So it says a material is required to manufacture office scissors. So a material for scissors. So scissors material. Scissors material. So that's the function. Then next, we are trying to determine the constraint. So for the constraint, it says here, paper is an abrasive material. So you're always using scissors to cut paper, cotton, or cloth. So paper is an abrasive material. So in order to measure abrasion is usually measured in terms of wear resistance. So if you want high abrasion resistance, you need high wear resistance. So one of the constraints is high wear resistance. Then after this one, then we can now read paper is an abrasive material and scissors sometimes encounter hard substances like staples. So in order for the material to withstand this staples, it has to be harder than the staple. So the material has to have high hardness. 2, high hardness. So most of the time, hardness is always proportional to wear resistance. So the higher the hardness of the material, the higher the wear resistance, because hardness is usually the ability of the material to withstand indentation or scratching. So in order for the material to be hard and wear, and usually most material that is hard is always usually brittle. But if the material is hard and brittle, it will break very easily. It has to break very easily. So we want a material that is also hard and also ductile at the same time. So that is measured in terms of toughness. A hard and ductile material is called a tough material. So we need high toughness. 3, high toughness. Then the next thing we need to think about designing this particular scissors. How do we design this material? In order to design scissors, we usually use forging and stamping. That's what we use, forging and stamping. And that means this material has to be able to be forged and stamped. So for able to be forged and stamped. So that's this. Then that's for the constraint. Then the objectives. For the objectives here, we see that after reading here, we can see list the function and the constraint. Set the objectives to minimize cost. So we are trying to minimize cost. Then our free variables. Is choice of material over here. choice of material. So that's our free variable. So now let's go to question 6.3. So for question 6.3, take a second, pause the video and read the question. So in this question, we are still determining the function, constraint, objective, and free variable. So for the function, which is usually in the first line of the question, a material is required for a heat exchanger. So heat exchanger material, that's what we are looking for. So that's what we're looking for, a heat exchanger material. Then next, whatever we are trying to get towards, the constraints. So the constraints are, if you're reading, a material is required for a heat exchanger to extract heat from a geothermally heated saline water. So a material that is dipped, it will be dipped inside saline water to extract heat from a saline, that's a salt water, at what, 120 degrees C. So it has to be able to what, extract heat from this material. So one, it has to be what, a good conductor of heat. It has to be a good conductor of heat. So good conductor of heat. That's one. Then two, a service temperature. It has to have a temperature, melting temperature above Tm. So above 120 degrees. So Tm should be greater than 120 degrees C. So it is not just Tm. It's not just Tm. It has to be what? A service temperature. It has to be service temperature, not just Tm. Because if you're heating up a material will start losing its properties for within a certain temperature range. So the temperature at which this material will start losing its properties should be what? Above 120 degrees C, not just the melting temperature. So that's number two. For number three, what else do we need? So you know that the material is dipped into what? Salt water. So corrosion resistance. So when you dip a material, because salt water enhances what? Corrosion. So it has to be what? Corrosion resistant. That's another one. So another one, you now think about and thus under pressure. So the material will still be under what? It's a specific pressure. So it needs to what? Be strong enough to withstand what? Whatever pressure that is being applied on it. So number four, high strength to withstand pressure. High strength to withstand pressure. Then the last one, you now think about forging this material. When you're trying to make this material, which properties do you need to make this material? And you know that heat exchangers are always in what? Pipes or in tubes. So it should be able to be either rolled or extruded into what? Pipes. So we should have what? High ductility to be rolled or what? Extruded. Number five, high ductility to be rolled or extruded. So that's all the constraints. Then the objective of this material, objective is what? To minimize cost. And the free variable is what? Choice of material. Material choice. So that's it for this question. Let us move to the next. So guys, for question 6.4, take a second, pause the video and read the question. So in this question, we are trying to find the function, constraints, objective, and free variable of this particular design. So first we have what? Function. Function. So the function is always in the design requirements. So a C-clamp. So that's what we are looking for. A C-clamp is required for processing electronic components at what? Temperatures up to 450 degrees C. So a material for a C-clamp. That's what we are looking for. Material for C-clamp. So that's the function. Then next we are looking for the word constraints. Those are things that cannot be negotiated upon. It has to be met. So these are what we are looking for right now. So it has to process, this material has to process what? Electronic components at temperatures up to what? 450 degrees C. So the service temperature of this material, T max, has to be greater than what? 450 degrees C. So that's one of the constraints. So the next constraint we shall keep reading. it is essential that the C clamp or the clamp has a low thermal inertia as possible. So low thermal inertia as possible. So this is part of what the objectives as possible, so that it reaches temperature quickly. So it has to get to the temperatures required as quickly as possible. So that's part of what this is also part of what the objectives. And it must not charge up when exposed to what an electron beam. So if you expose a material to an electron beam, in order for the material not to charge up, it should be able to what conduct the electron beam through the material. So another objective is what it has to be conductive in order to prevent what charging. That's another one, has to be what conductive. So that's one. That's another objectives of this material. So also, if you're looking at the function of this C clamp, you're going to use this C clamp to tighten a material or an electronic device as hard as possible. That's how you're going to hold the material. So for this material to withstand these forces, it should have what the required strength. It must have the enough sufficient strength to what withstand what tightening this material onto what electronic devices. So it has to what have what sufficient strength. Has to have sufficient strength. So that's the last what constraint. Let's look at what objectives. So the objectives of, so this is the constraint, this is the function, this is the objective. So if you're looking at here, they said the objective of this G clamp is to make sure that the thermal inertia is as low as possible. In order to reduce this thermal inertia, the temperatures, the time that it takes for the temperature to get to the equilibrium temperature must be very small. So if you look at this relationship that they gave us here, so T is the time it takes for you to get to what equilibrium temperature. So we are trying to what minimize this time, because we are trying to make it to reach the temperature as quickly as possible. So in order to minimize this time, you need to what either minimize what A, and A is giving us what diffusivity. So diffusivity is what a material property. So we are trying to what reduce the diffusivity of this material. So the objective is what minimize. Oh, sorry, we are trying to what maximize diffusivity, because if you increase this value, then the time it takes will be reduced. So we are trying to what maximize what diffusivity. So maximize diffusivity. So for the objective, we are trying to, if you look at here, they said what, let us reduce what thermal inertia. We are trying to what reduce thermal inertia as quickly as low as possible. But in order to do this, the temperature has to get to the equilibrium temperature as quickly as possible. So we need to what increase this value. We need to what reduce this value. Sorry, we need to reduce T, the time that it takes to get to what equilibrium temperature. We need to what reduce it as low as possible, So in order to do this, we need to what increase this value A, based on this relationship, and A is giving us what thermal what diffusivity as A. So the objective of this question is what increase thermal diffusivity. If you increase thermal diffusivity, then you can now what reduce the time to reach equilibrium, and therefore what reduce what thermal inertia. That means we are trying to what maximize diffusivity. We are trying to what maximize diffusivity. Then the last one is what free variable, which is given here. The free variable can be what choice of material. So let's move on to question 6.5. For question 6.5, take a second, pause the video and read the question. In this particular question, we are looking for the function, constraints, objectives, and what free variable for this particular design. So first, for the function, that's the first thing that we are looking for. Let us read the question. A furnace is required to center powder metal parts. It operates continuously at 650 degrees C while the parts are fed through on a moving belt. You are asked to select a material for furnace insulation. Select a material for what? Furnace insulation. So the first, our function is what? Furnace insulation what? Material. So furnace insulation material. So that's the first, that's the function. Then for the constraint, these are things that must be met. It cannot be negotiated upon. It must be met. So first it says it operates continuously at a temperature of what? 650 degrees C. So the maximum service temperature, the service temperature T max must be greater than what? 650 degree C. So that's the constraint, one of the constraints. This is one. So another constraint 2, the second constraint over here. Let us read the question and see if we have what more constraints in this particular question. So you are asked to select a material material for furnace insulation to minimize heat loss. So if you look at here, we have already encountered what the objectives: minimize what heat loss, and make sure that the furnace energy is sufficient as possible. So make sure this furnace energy. So if you minimize heat loss, you're trying to make sure that furnace energy is what sufficient. Then for reasons of space, so for reasons of space, the insulation is limited to a maximum thickness of what 2 meters, 0.2 meters. So the second one is what maximum thickness, the thickness T of the material, or X. In this case is X. In this case is X. So X should be greater or should be less than or equals to 0.2 millimeters. So it has to be limited to 0.2 millimeters. So that's the constraint. So these two are the constraints. Then the objective. So if you look here, we encountered the objective before. It said minimize heat loss. So in order to minimize heat loss, in order to minimize the heat loss of a material, it has to what? You have to what? Minimize what? Thermal conductivity. So the less conductive the material is, then you're minimizing what? Heat loss. So minimize thermal conductivity. So that's the objective. Then free variable is what? Choice of what? Material. So that's that. Let us move on to question 6. So for question 6.6, if you take a second, pause the video and read the question. So here we are looking for, same as the other questions, function, objective, constraints, and what? Free variables. So first, function. So if you read the question, it says that we are looking for a material for an ultra precise bearing that allow a rocking motion that makes use of what? Knife edges or what? Pivots. So we are looking for a material for what? Ultra precise bearings. So material for bearings. So that's the function. Next, we have the what? Constraint. So that's the next thing that we are looking for right now. So an ultra precise bearing that allowed a rocking motion makes use of what? Knife edges or pivots. So if you look at this diagram over here, so the knife edges makes what? A rocking motion, and it tries to what? Scratch on the what? Block. So that it makes a rocking motion, it tries to what? Scratch on the block. So that's what is going on, right? So it says as the bearing rocks, it rolls, translating sideways by a distance that depends on the radius of contact. So based on this radius of contact R. So the further it rolls, the less precise its position. So the further it rolls, the less precise its position. So you don't want this this bearing to roll so much. So you don't want it to roll so much. So they said here, so the smaller the radius of contact R, the better. So you are trying to what? Reduce R. So this is now part of what? The objective. The smaller, the better. The smaller the radius of contact, the better. Then they now said here, but the smaller the radius of contact, the greater the contact pressure. So if R, let's write a relationship. So R is what? Inversely proportional to the pressure P. So if you make this smaller, then this the pressure becomes very high, the greater the pressure. So you want to reduce, in what sense? If you're trying to what? Reduce this R, you're trying to what? If you're reducing this R, you're trying to what? You're increasing this what? P. So that's the thing. If you're reducing R, you're increasing what? P. So you don't want P to reduce at the end of the day. So they said, but the smaller the radius of contact, the greater the contact pressure F over A. If this exceeds the hardness of either material, because the materials are pushing against each other, if it exceeds the hardness of each material, it will be damaged. So you don't want this damage to happen. So in order to prevent all this from happening, you need a material with a what? A very high what? Hardness. So the higher the hardness, the low you can make R as low as possible, but because it doesn't matter. So if the material is so hard, even though R is as small as possible and P is now as great as possible, it will not matter. So your objective here is now what? You're trying to what? Increase the hardness of the material. So let's just write objective first. Objective, you're trying to what? Increase or maximize. Let's say maximize. Increase is not the right word. Let's say maximize what? Hardness. That's our objective in this particular question right now. So that's the objective. They said okay, where did we stop? We saw here if this exceeds the hardness of H of either face of the bearing, it will be damaged. So that's why we are trying to increase the hardness as high as possible. Also, elastic deformation too is bad. We don't want the material to elastically deform. So in order to prevent elastic deformation is defined in terms of what? Young's modulus. So the higher the Young's modulus, the less elastic deformation. So we want to what? High elastic or high Young's modulus. Young's modulus. So that's one of the constraints. So if you continue reading, it says a rocking bearing is required to operate in a microchip fabrication using fluorine gas at what? 100 degrees C. So the surface temperature, the maximum surface temperature T max, has to be what? Greater than what? 100 degrees C. So that's another one. And it's working on in what? A fluorine gas environment. So the material has to be what? Resistant to fluorine gas. Resistant to fluorine gas. So that's what we are trying to do. We are trying to resist fluorine gas. So that's what we are trying to do, resist. So we have our function, we have our constraints, and we have our objective. So if you continue reading, it said followed by e-beam. So there is a beam that is beam processing requiring a structural part of the equipment. So you want the material to process this e-beam. So there will be a beam on this material. So you need a good conductor. So this material has to be a good conductor. So that's all our constraints right now. So our free variable in this material right now, free variable is now what? Material choice. Yeah, so that's it for this question. If you have any question based on this, just let me know in the comments. So for question 6.7, if you take a second, pause the video and look at the question. So this question as well, we are trying to determine function, constraint, objective, and what? Free variable. So first, if you read the question, let us determine what? The function. So the function, the standard CD, that's the jewel case, cracks easily. And if broken, it can scratch the CD inside. So if the case of the CD is broken, it can scratch the CD inside, and you don't want this. So jewel cases, these are the cases that are used for the CD, for regular CDs that we have. Jewel cases are made up of what? Are made of injection molded polystyrene. So usually the material used for these CDs are what? CD cases are what? Polystyrene. Chosen because it is what? Transparent, cheap, and easily molded. So a material is sought to make CD cases. So the function is what? Material for what? CD cases. So material for CD cases. So that's the function. Then let's look at the constraint. So for the constraint, so first, the main problem of the formal CD cases for the ones made with polystyrene is that it cracks easily. It cracks, and we don't want it to crack. So any material that we choose must have a what? Higher fracture toughness than what? Polystyrene. So it must have a fracture toughness greater than what? That of polystyrene. That of polystyrene. So that's one of it. Then the next one says it has to be molded. So they use injection molding to make it before. So it has to be injection molded. So able to be injection molded. So that's one. That's another one. So the last one is it has to be what? Transparent. If you look at here, a material sought for this must not crack easily. The case must also be what? Transparent. That's one of the requirements. It must also be what? Transparent. So transparent is one of the constraints. So next, we now go to what? Objectives. So for the objectives, it says that we choose polystyrene before because it is cheap. It is cheap. So if you can make this material as cheap as possible, that would be perfect. So we are trying to make this material as cheap as possible. So we are trying to minimize cost. Then our free variable is what? Choice of material. So that's our free variable for this question. So now let us move on to the last question in this series. So for question 6.8, the last question in this series. So we have a storage heater, take a second, pause the video and read the question. So the same thing like others, we are looking for the function, constraints, objective, and what? Free variable. So for the function, let us read the question. A storage heater captures heat over a period of time. Then it releases it usually to an steam when required. Those for domestic heating store solar energy or energy from what? Chip off electricity and release it slowly during the day, during the cold part of the day. Those for research release the heat to a supersonic air steam to test system behavior in supersonic flight. So you're saying, what is a good material for the core of a compact storage material capable of what? Temperatures up to what? 120 degrees C. So we are looking for a material for the core of a compact storage system. So material for the core of a storage system. So the material for the core, that's the word we are looking for. And now for the constraint. So you know the purpose of this material is to what? Store heat energy. To store heat, that's the main purpose of this material, to store heat energy. So the property of a material that tells you the ability of the material to store heat energy is called what? The specific heat capacity or the heat capacity of this material. So the higher the heat capacity, so that this is measured in what? CP. So the specific heat, so higher high heat capacity. So the material must have what? High what? Heat capacity. So that's one of the constraints. Then another constraint, the material must be capable of what? Temperatures up to what? 120 degrees C. So the service temperature T max has to be greater than what? 120 degree C. So that's the constraint. Then the objectives. So the objective, there is no clear objective here, but it says that they are trying to use it for what? Either domestic heating or for supersonic flight. So if you can make it as cheap as possible, so it should be good. So it should be as cheap as what possible. So we are trying to what? Minimize cost of the material. Then the last one is what? Free variable, which is what? The choice of what? Of material. So if you have any questions, please let me know in the comment section, and please comment on this video so I know that I'm doing everything right. Just let me know in the comments. Don't forget